Hello friends, and welcome to Webronaq. Imagine waking up at 3:25 in the morning and finding Facebook completely unreachable. Not for you, but for tens of thousands of people all at once. That is exactly what happened yesterday, on July 19, 2026. According to Down Detector, more than 23,000 US Facebook users and at least 18,000 US Instagram users filed outage reports in under 90 minutes. An analyst cited a glitch during a planned update as the most likely cause. NetBlocks confirmed it was not a country-level internet disruption. And here is the detail that matters most for engineers. WhatsApp, owned by the same company, was largely unaffected. That contrast is the whole lesson. Today in this video, we are going to unpack exactly why that happened and how you can build systems that survive the same kind of hit. So why did Facebook and Instagram go down while WhatsApp kept running? The answer comes down to a concept called cascading failure. A cascading failure happens when one broken component causes dependent components to fail in sequence, like a crack in a load-bearing wall spreading through a building. In this case, analysts believe a glitch during a planned update affected a layer that Facebook and Instagram both depended on. Because those two platforms shared that dependency, the blast radius, meaning the area of damage, reached both of them at once. WhatsApp runs on a more decoupled update path, so the fault never reached it. This is the core danger of shared dependencies in distributed systems. You think you have two separate services, but underneath, they are drinking from the same well. When that well breaks, everything connected to it breaks together. The fix is architectural, and it starts with a pattern called graceful degradation. Now that we know why cascading failures spread, let us talk about how well-designed systems contain them. The first pattern is called graceful degradation, and the idea is simple. Not all features are equally important. When part of your system breaks, you shed the non-critical parts and keep the core user journey alive. Think about what Meta could have done differently. When a back-end recommendation service struggles, instead of throwing a hard 500 error and showing users nothing, a gracefully degrading system quietly skips the personalized feed suggestions, and the reels refresh. The user can still scroll, still post, still message. The experience is reduced, but it is not broken. The key engineering decision is made up front. Rank every feature by how critical it is to the core journey, and design explicit fallback behavior for each non-critical one. A degraded experience beats a dead one, every time. Next, we need a mechanism to actually stop failing calls at the source, and that is where the circuit breaker pattern comes in. Alright. So graceful degradation decides what to serve when things go wrong. The circuit breaker decides whether to even attempt a call to a struggling service. Think of a real electrical breaker in your home. When too many faults hit a circuit, it trips open and cuts the flow. In code, a circuit breaker wraps every remote call and tracks failure rates. Once failures cross a threshold, say 50% of recent calls, the breaker trips to the open state. Now it stops sending calls to the sick service entirely. Instead, it returns an instant fallback, a cached result, a safe default, or a short error message. No thread hangs waiting for a timeout that will never succeed. After a cooldown, the breaker moves to a half-open state and sends one probe call through. If that probe succeeds, the breaker closes and normal traffic resumes. If it fails, the breaker stays open. Next, let us make sure one struggling service cannot consume every thread your app has. Now here is the interesting part. Even with a circuit breaker, a slow service can silently exhaust all your threads before the breaker trips. That is where the bulkhead pattern comes in. The name is taken directly from the watertight compartments inside a ship's hull. If one compartment floods, the sealed walls protect the rest. In software, a bulkhead assigns each downstream dependency its own separate thread pool. Your recommendation service gets 10 threads. Your messaging service gets its own pool. When recommendations collapse and consume every thread in their pool, the messaging pool keeps running completely untouched. You can see exactly this principle at work in the July 2026 Meta outage. WhatsApp sat in its own isolated resource lane, insulated from the update that overwhelmed Facebook and Instagram. That separation is precisely why it kept running. Isolation is not an accident. It is a deliberate architectural decision, made long before anything breaks. Now let us wire these patterns into real production code. So let us bring it all together. Resilience 4J 2.4.0 is the recommended library for these patterns in modern Java. In a Spring Boot 4.1 project, 2 annotations do the heavy lifting. The @circuit breaker annotation wraps any service call and manages the 3-state machine automatically. The @bulkhead annotation caps the concurrent thread count for that specific dependency. Resilience 4J exposes circuit state and rejection metrics out of the box, and Prometheus scrapes them. Pipe those into Grafana 13.1, and you get a live dashboard that shows the exact moment a circuit trips and how long it stays open. Here is the mental model to carry forward. Failure is not an edge case, it is the expected default in distributed systems. The July 2026 Meta outage showed once more that even hyperscalers can fail at a single shared layer. Build your compartments before the flood, not after. Thanks for watching, and I will see you in the next one on Webronaq.